Hey y'all. So I want to talk about lambda calculus in semantics. So I'm going to assume, for the purpose of this video, that you are familiar with the with functions. So there's this old functional notation that we use prior to using lambda calculus, and lambda calculus kind of aims to simplify that. I also assume you know what meaning is and how we use the principle of compositionality. If these are not familiar, then you might want to go find videos and learn about them. I'm not going to cover them in this video. Maybe I'll touch it on in a future video. So let me switch screens, and we have some sample work that we can kind of look at. And the first thing I want to do is I want to talk about lambda notation, the syntax of using making a lambda function, and kind of why we use it. So the idea is that we're simplifying it. So there might be an example somewhere down. Maybe not this one. Let's look at lecture 7 handout. Let's look at this one. Yeah, so this is a good example of a a function. So we have our domains, and then it's like a nested function in that this returns a function, and this function returns a truth value. You can kind of see how cumbersome it is to read, and the objective is that we want to simplify this. And so I like some of the examples on here. So basically, all you need to know is we put lambda, and this kind of tells it's a lambda function. We give it a name for the variables. So I'm going to do x, but maybe sometimes I do p and q versus x and y, just to switch it up. First thing you do, put a colon, and the colon is where you're going to specify the domain. So I'm going to say p in the set of 1, 2, and 3. So this is the domain of our function. And then we can give it, I forgot what this is called, the value description. So this is what we basically do with our input. So I'm going to say p plus 1, right? So basically what this is saying is that for the values, for values in this domain, so in this between 1 to 3, we can get an output by calculating p plus 1. So the possible values that we can insert in this function are 1, 2. So 1 gives us an output of 2 because p plus 1. Then we have, 2 and then 3. And then finally 3, 4. And that's basically what this statement says. So for right now, we don't know. So we don't know what our input is. So these are all the possible, this is the set of, possible value pairs, ordered pairs that we have by this function. So if you look at this function, these are all the value pairing that we can ever have with this function because of this function. But say we were to give it an argument. Say we gave it 2. It would simply give us back 3 because that is the ordered pair. This is input, this is output. So let's take this and let's apply it to, one of these practice problems. So we have something like this. So this is a function with nested functions. So we have 1, 2, 3. We have 3 lambda functions kind of nested within each other. And the way I like to approach it is, so the very first thing we do is when you have arguments, they are always outside and they're kind of in parentheses. So your arguments are going to be in parentheses. The functions themselves are going to be in square brackets. If you only have one function, unless it has arguments, you're not really going to see the square brackets. So like what we drew before, whatever, this is all there's no argument, so there is no square brackets. But once you do, you kind of want to delineate those, and that's why we have the square brackets coming into play. We also have nested functions, so we want to show the boundaries between functions, especially. So what we do is think of functions as kind of boxes. That's kind of how I like to think of it. That's kind of related to computer science, where we have our outermost function, which is lambda y. We have our slightly inner function, which is going to be lambda x. And then we have yet another one in here that's lambda z. So those are our 3 functions, and we're going to look on the outermost. So think of these arrows or this bracket. So you see how there's matching one in the beginning and the end? That's like the parameters, that's like the boundaries of the outer function. And what we're going to do is we're going to pass this argument, which is to the right of it, immediately to the right of it, and look for a lambda function. Now notice that in this case, we don't see a lambda. There is no lambda function in this outer scope. So really what it looks like I messed up a little bit. It doesn't actually look like this. It looks more like, okay, there's nothing in the outer one, but in the inner one there is a lambda y, and then there's a lambda x, and then inside here we have a lambda z. A little bit more tricky. See, so really pay attention to these, the scope, as I'll call it. So Felipe is not an argument to a function. Felipe is going to this box, but we can't actually apply it because there's no function to apply to. So we're just gonna, put a pause on Felipe for a second, and we're gonna look inside the second layer. So not this first one. So we're just gonna cross it out for now. So now we have Catherine and we have lambda y. And so what we're gonna do is we're gonna take Catherine and we're gonna plug it into this function. So Catherine is going into here. So Catherine's in lambda y, and what we're gonna do to make things simple is we're gonna cross out that function because we have applied it, and we are gonna plug in Catherine for where there's a y. So now our statement will look like this. So lambda x of type E, and then we have lambda z of type E, and then Catherine, I'll just abbreviate as K, talked to z about x. And now here's our closing, and then we have George after here. So George. And then we have our final two brackets. So now we can kind of cross out Catherine, and this is kind of what our thing looks like right now. So now we kind of do the same thing. So George is gonna be applying to this lambda x. So we'll put George here, and we can do the kind of the same thing. So we go here and plug it in. Now something I should probably have noted is that this notation where it's like lambda x of E, this is the same thing as, lambda x, and then x is in the set of, domain of, and in the set of entities. Remember, these are primitive types. So we have E and we have T for truth values, E for entity. But a shorthand notation is to just put it as a subscript. So that's what that means. So we are actually also doing checks on, if our input is in the domain. It's kind of like input validation. And in these cases, they are. George is an entity. So we can apply it, and I put it to the wrong one. It should be going to X here. So because it does apply, we're going to cross this out, and we're going to replace X with George. So now our sentence, so ignore this stuff. Our sentence is lambda x or lambda z of type E. Catherine talked to Z about George, and I'm going to abbreviate as well. So now we have satisfied Catherine, we've satisfied George. We still have Felipe. What happened to him? Well, Felipe is still on the outside. There's still a Felipe bracket. We kind of crossed it out. He's still there. He's in this outermost scope. And because these both have satisfied their arguments, this one kind of carries down, and will apply to Z because that's the remaining function. And it hasn't got an argument, but we have an extra argument in the higher levels. So now Felipe comes into play. So we'll put our brackets, and Felipe, and then he's going to plug in. Is he an entity? Yes, he is. So now we're going to cross this out, and we're going to replace Z with Felipe. So our final sentence that we get, our final statement is, Catherine talked to Felipe about George. And that is kind of the basic overview of, Lambda calculus. And to drill this point even more, let's do another example. In this example, I want to do one from this handout. So kind of working backwards, because there's a very interesting exercise, if I can find it. Hold on. I believe it is here. So what happens, so let me zoom in a little bit. So what happens if we don't have enough arguments? So I'm looking at 26b here. So we only have one argument, which is Minnesota, and that's it. But notice there are two functions. So, what can we do? Well, let's take a stab at it. So we're gonna do kind of the same logic. So notice this doesn't have that shorthand. This is the full written out way of defining the domain of a function. But it's really equivalent to what we saw before. So Minnesota, and we're gonna go to the outer level. So let's draw the boxes. So we have a big box, and that's going to be lambda y. And we determine these boxes by looking at the brackets. So the biggest box is going to be lambda y, and then inner box is going to be lambda x. And we can look. Okay, so Minnesota, we kind of bring it here, and it's saying there's this variable y, which is in the set of z for z is a U.S. state. So what this basically means is y a U.S. state? And Minnesota, as far as I know, is a U.S. state. So check, that is good to go. So what we can do is we can now cross this out, and wherever we see a y, we can substitute Minnesota. So now I'm gonna erase this for, complex, just for space. Now we have the following, and then this will be Minnesota. This is the following, statement that is left behind. Now notice we don't have an argument here. So what do we do now? Well, we don't have any argument, but we can still make a statement. So we can say, well, there's some variable x, and there is no argument for it, so we're just going to treat it as a general case. So x is in the set of z for z is a city. So we could interpret this as x is a city, and then we can complete the statement in Minnesota. And that would be the statement that we get from this function. Now, of course, if we had another, if we had Duluth like up here, then we could plug that in and we could get Duluth is a city Duluth is in Minnesota. But because we don't, we kind of generalize it out by saying x is a city in Minnesota. So we kind of like resolve this into a general statement, then we plug it in for x. So that's that's basically the foundations of lambda calculus. Now this is not the easiest thing, it's not the most intuitive thing, so it will take some practice. And make sure you are paying attention to the brackets. Like you saw what I did, I got a little confused on that first problem because I didn't pay close enough attention to the brackets and I had the function in the wrong box. So just pay attention, go slow, and you'll be doing this in no time. All right, I hope that was helpful. If you have any questions, leave them down in the comments. I will answer them. Awesome. Get out of here.